Hello, student. Today the lecture of electric charges and field is number three, and till now we have covered a major portion of electric charges and field. We have seen that what are electric charges types and what is actually an electric charge and how the method of charging are like what are the method of charging are like induction, conduction, like that. And then we have seen types of conductors and insulators. After that, we have seen about properties of charges, and then we have seen electric field and what is electric field actually. Also, we have seen that what are the conditions for or properties of like electric field, some properties we have seen, and electric field in vector form we have seen also. Okay. Also, we have seen Coulomb's law, that is very important. Today we will continue our lecture in the that manner, and where we have completed in the second lecture. After that, we will proceed. So, I hope that you all are aware of the syllabus and what I am teaching here. That this is for only CBSE board students and not for JE or like that. For that, we will cover in next sessions or in the upcoming sessions. But this is primarily focused on your boards exams for class 12th. And yeah, let's continue. So let's see the example 9. So we have just terminated our lecture before electric field due to system. This was the last topic. So now we will see that what is this example 9 in your book. So it is given that two charges plus q and minus q are kept at points minus x2 comma 0 and x1 comma 0 respectively in the xy plane. Okay. So there are two charges that are plus q and minus q, and they are kept at points that is minus x2 comma 0 and x1 comma 0. Okay. In the xy plane. That is the plane. uh, XY is the plane, not in 3D, but it is a plane. So find the magnitude and direction of net electric field at the origin. So we have to find the net electric field and its magnitude and direction as well as. So we have to see that what is the value of that. So to find this electric field intensity at a point due to charges, we have to find the individual electric field due to both charges, and then the resultant field will be calculated by adding the electric field due to each charges vectorally. Because electric field is a vector quantity, so we will add them separately in the final step, step, and that will be vectorally added. Okay. So here you can see in the figure that the at A point the charge plus q is kept, and it is a point minus x2 comma 0, and this is origin. This point is origin, and here E1 and E2 are the directions, which I will tell you right now. Please just focus on here that the charge minus q is kept on x1 comma 0. Okay. So if you have to find the electric field at the origin, the direction of electric field due to x1 comma 0 charge, that is minus q, should be in the direction of 0, because I have already told you in the previous lecture that the direction due to negative charge of electric field direction to negative charge in inward direction, so it will be in inward direction due to this charge. It is coming inward to this charge. And for plus q, the electric field direction would be in the direction like this, like outward direction. So it will be in the direction like this. So this is E2, and this is your E1. Okay, it is E1 and that is E2. Now electric field intensity at point O due to plus Q charge. I have to calculate the magnitude of that electric field. So that will be equal to what? KQ by X square. And what is X here? X2. This distance is X2 from origin. So it and the the value will be equal to KQ by X2 whole square. And its direction will be towards P. Okay, towards P is the direction which I told you for in the previous topic that it will be in the direction like this. So its direction will be towards P, and electric field intensity at point O due to minus Q charge will be E2. That will be okay. That will be denoted by E2. So they have taken that a point A charge has the electric field E1. So I have told that it is E2, but it will be E1. Okay. Don't worry, that will be like direction of both the electric fields would be in the same direction, but one is E1 and one is E2. Okay, so E2 will be what? This is due to minus Q charge, and its value will be equal to KQ by X1 square, because the distance between the origin and B charge is X1. Okay, so that is why it is KQ by X1 square, and its action is also towards P. Both the charges have the direction of electric field will be in the direction towards B, and now E1 need to act along the same direction. It is given also here. So let's move to the next slide and clear this. Yes, just a second. Okay, so net electric field intensity at point O, that is origin, is given by that will be equal to E1 plus E2, because the directions of both the vector of E1 E2 will be in the same direction. So we can just add them uh, straight away we can add them. So it will become equal to KQ by X2 square plus KQ by X1 square, and direction will be towards the B. And after simplifying, we will get it KQ by into 1 by X2 square plus 1 by X1 square. So this is the your final answer that is given here. So it was a simple question, but you have to aware of the directions. Okay, so example 10 is given here. So this is also a good example. So let us find out what is saying. 2 point charges plus Q and 4Q plus 4Q are separated by a distance 6a. Okay. Find the point on the line joining the two charges where the electric field is zero. So we have to find any point on the line joining two charges. So a line joining two charges. So the a point on the line joining two charges can be on between them. Like the point can be between the two charges, or it can be away from the two charges, like in the right hand side or left hand side. So we have to see that where it is a charge placed. Okay. So we have drawn here that plus Q is there and minus plus 4Q is there, and the distance between them is 6a. So suppose that we have the point P as the this point is the that point we have the electric field value, net electric field value due to both charges will be equal to 0. Okay. So if the point P has the net electric field equal to 0, so electric field due to this, because okay, so I will clarify that why we have chosen here the point between the two charges. Why we have not chosen the point behind this charge or behind this charge? Because if I choose the point here, P, then the direction of electric field due to this will be in this direction, and due to this will be also in this direction. So how can the electric field will be here 0? Because they will add vector only, na? Because they are all in the same direction. Similarly, for that point, the electric field direction due to this charge will be in this direction, and this charge will be also in this direction. So they will add here also. But if the point is in between the two charges, then the electric field due to this charge will be in this direction, and this charge will be in the opposite direction, and they will add out to and cancel out their effect, and the net electric field will at that point will be equal to 0. So I have chosen this point P as a reference, like where the electric field, net electric field is 0. So if I write the equation of like KQ by X square, that is equal to, because a distance between the plus Q charge and this point P is X, I have taken it X. So it will become 6a minus X. This distance will become 6a minus X. Why? Because the whole distance between plus q and 4q is 6a. So if this distance is x, this will be 6a minus x. So here the value of electric field for plus q charge. Due to plus q charge, the electric field value will be like this: aq by x square, simply kq by x square. And for this charge plus 4q, that will be equal to k4q upon 6a minus x square. Because the distance now becomes 6a minus x between the P point and this 4q charge. So that is why we have written like this. And we will equate the electric field both sides, like due to plus q charge and 4q charge, both the electric field should equate themselves and will be equal because they are nullifying each other. That is why we have equated them. So from here we have got the equation 1 by x square is equal to 1 by 4 by 6a minus x square. After simplifying, we will get 1 by x because we have taken a square root both sides. So it will become 1 by x is equal to 2 by, this is 4. So square root of 4 is 2. 2 by 6a minus x. We have taken positive values only because the distance will be in positive term. It will give positive value only. If you have taken here negative term, then it will give you negative value of x. Okay. So x will come out to be equal to 2a. So this is the answer for your question, that x is equal to 2a. So the electric field where the point where the electric field will be 0 will be equal to 2a distance from plus q charge. From plus q charge, the distance of that point P is 2a. Okay. At this point, the electric field due to these charges, net electric field due to these charges will be equal to 0. I hope you got this question. And it was a simple question, but you have to be careful that where the point should be taken, whether it is behind the other charge or it will be between the two charges. Okay. So let's move further and delete this slide. Okay. Yeah. Physical significance of electric field. So what is the meaning of physical significance of electric field? Okay. He will see here that what are the properties of like electric field lines and what is the physical meaning of electric field, and whether they are what are the nature of their like electric field lines, and we will see here. So let's move further. Okay. Yes. So electric field line in a general is a curve drawn in such a way that the tangent to it at each point is the direction of the electric field at that point. So I hope that you got this point, that a field line is a space curve, that is a space curve in the three dimension. So if you have plus q charge, so the electric field lines are like this. Yeah, I have already told you, like electric field lines will be like this. Yeah. So if you is a curve drawn in such a way that the tangent to it at E point is the direction of electric field. Okay. So electric field will be what? That it will give the tangent at any point. So if you draw tangent here, it will be in the same direction. So that will give the electric field direction of this point. Okay. That is telling me here. Electric field lines are thus used to pictorially map the electric field around the charge as a configuration of charges. Okay. So that will give you the electric field direction at any charge distribution. Let's move further and see other properties of this. Okay, one point is here written. We have to be careful and be aware of this point, that if the density of field lines, like if I have any charge here, if I have charge A here, if I have this charge, and the density of any field lines, like if the field lines are denser here, so this at this point the strength of electric field is very high. But at this point, the electric field lines are farther away and density is lowering. The density of electric field lines are weak here, so the field will be also weaker here. Okay, field will be weaker here, and here the field are like strengther or that like they are more. Okay, so be aware of this point that at field lines where they are dense, the electric field value is also higher, or the strength of electric field is also higher there. And where the electric field lines are not denser, so that at that point the electric field strength is weak. Okay. Now some properties of electric field lines. What are these? Let us find out. So electric field lines start from positive charge and end at negative charge. That I already told you that the direction of electric field lines are like outward from positive charge and inward from minus Q charge. So it means that electric field lines start from positive charge and end at negative charge. Or it's showing that it means actually that only. In case of single charge, they may start and end at infinity. So if you have like dipole charges, so it will be dipole. I will talk in later on that what is that. If you have like two charges, then it will start from here and end here. But if you have only single charge, if you have only single charge like plus Q, then it will start from here and end at infinity because there is no other charge. So the electric field lines will go farther away and end at infinity. Okay. Tangent to any point on the electric field line shows the direction of electric field at that point. That I have already covered in the like previous topic that a tangent at any point on electric field will gives what direction of the field at that point. Okay. Two field lines can never intersect each other because if they intersect, then the tangent drawn at that point will be given two direction of field at the point. So this is very important point that if there is a electric field lines due to charges, if are they like this, but they will not cut each other. They will not cut each other. Like we cannot get the electric field lines like this because if you draw tangents here, then there at the single point you get two tangents. It shows that there are two directions of electric fields, but it is not possible for a single point and having a two direction of electric field, two directions of electric field. Okay, so it is practically not possible for an electric field to cross, cross each other. Two electric field lines can never cross each other, and if it happens, then it shows two direction of electric field at a single point, and that is not possible. So yeah, these are 3 points which we have just now covered in the properties of electric field lines. Now we will see that what is the fourth point. In a charge-free region, electric field lines can be taken to be continuous curves without any breaks. Okay. So if you have a charge-free region is there, so electric field lines can be taken to be continuous curve without any break. Okay. Like you don't have charge region. So electric field lines will be like this, parallel to each other. Okay, without any break will be there. No break will be there because there are no charges in the free region. The electric fields are like this. It is telling this point. Now fifth point is what is that? Electric field lines do not form closed loop because of conservative nature of electric field. Okay, so this point is very important. That electric field lines do not form closed loop because they are conservative nature of electric field. Conservative is what means that you have if you have like work done due to closed curve and at 2 points A and B, like if you have work done from this path and this path and this path, so all work done will be same. Work done at a closed curve, work done at any path due to closed curve will be same. So it is a conservative nature of electric field. So if a field is like conservative, it doesn't form a closed loop. If a magnetic field is there, that will form a closed loop, but electric field do not form a closed loop. So that should be clear to you. Okay. At now 6 point is electric field lines are perpendicular to the surface of a charged conductor. Okay. So if you have a conductor there, like spherical conductor, so electric field line doesn't go like this. They will be like perpendicular to this surface. like they will form perpendicular like this. Okay, surface, they will be perpendicular to the surface. Near the surface, they will be perpendicular to the conductor. Always they are perpendicular to the surface of a charge conductor. That you will see in the detail, like in we will see in detail in the conductors we will when cover the conductor topic. And yeah, this point is 6 point. And what is the 7 point? Electric field lines contract lengthwise to represent attraction between two unlike charges. Okay, so electric field lines they contract each other. Uh, Means that they are managed to change the length of themselves, like electric field lines. If the attraction between two unlike charges, if there is a like two unlike charges are there, plus q and minus q, then electric field line will contract each other, like they will come together in the vicinity like this. And that will show what? That will show that they can adjust itself. So that is telling by this point. And 8 point is what? Electric field lines exert sideways pressure to represent repulsion between two like charges. Okay. So if like charges are there, so electric field lines exert sideways pressure. Like they will in sideways of this, they will exert a pressure. Here they will exert a pressure. Okay. So like this. 1 second. I have drawn it not correctly. Just a second. Yes. Like if you have a plus q and plus q charge, plus q and plus q. So electric field lines will be like this. Uh, those two. Like this. Field lines will be like this. Okay, so their sideways pressure is there. Like these are pressuring themselves to go is like asymptotic like that. They will not touch each other, but they will be asymptotic like this. And that is showing what? Sideways pressure to represent repulsion between two charges. So there is repulsion, and field lines are going away from each other, and that is showing repulsion between them. Okay, so these are some properties of electric field lines, and I hope that you got the point that what are the properties of electric field lines. And you will see the next topic now. Let's remove these drawings and move further in the representation of electric field. Okay. So for different types of electric field lines, they are represented as shown. So electric field line due to a uniform field. If you have a uniform field, that means that the gapping between electric field lines should be uniformly, and that they are very balanced and symmetric to the plane. Okay, so I will show you that how they look like. Here it is given also. They will be parallel to each other, and there is equal spacing between each field line. So this will show what? Due to a uniform field, means that will not change with time. Okay, uniform field will not change with like space. Okay, not change with space. Got it. So now electric field lines for a non-uniform field. If you have a non-uniform field, so like they will that is changing with the space. Like, means that will change with the your value like direction. So if you have a non-uniform field, then the electric field lines are like wavered. That will be like this, like this. Okay, that will not be parallel to each other, and the spacing between them will be also not uniform. So that will show what? That will show you a non-uniform field. Now, due to point charges, I have already told you positive and negative charge. That direction of electric field lines are outward, from positive charge, and inward to negative charge, point charge. Okay, radially, that will be radially. So that are some types. Let's see that what is the next topic. So let's move further. Uh, So one point is given in your book that it is a misconception that the path traced by a positive charge is a field line. So it is a misconception between the people that the path traced by any positive charge is a field line, but it is not a field line. The field line we have already like covered that what is a electric field. So it is a field line is what? It is a test charge. What the path covered by a test charge is a field line. Okay. So there is example 11 given, which is simpler one. So I hope that you will cover it by yourself. And let's see that what is the next topic in your book. So conductors in an electrostatic field. Okay. So electric field lines do not pass through a conductor, hence the interior of the conductor is free from influence of electric field. Okay, so it is a very important point that electric field lines do not pass through a conductor. It will happen due to self charging of or you can say shielding effect due to conductors, because the field electric field lines, if they pass through the conductor, so it will generate like opposing and equal electric field lines through them, and that will cancel out the electric field lines inside them. So net electric field inside a conductor will become zero. So that point is clear that why electric field do not pass to the conductor, because the net electric field due to shielding effect becomes zero inside a conductor. We will see that in later. Electrostatic shielding, that is given in your level, that it is called electrostatic shielding. Okay. Yeah. So it is shown here that electric field lines are like zero inside a conductor. Total charge of a charge conductor lies at the outer surface of the conductor. Okay. So if I give any charge to conductor, like if I give any charge to conductor, it will reside at the surface of the conductor. Why? Because they have the content, like they have the tendency to they want themselves the positive charge. They want that they should remain at the farthest point from each other. Like if you give them positive charge, so they will repel each other, because there are very much free electrons also inside the conductors. So they want themselves to repel each other, and they will goes away from themselves, and goes farther away where they can stable themselves. So the farthest point that where they can go is like on the surface. There the distance will be maximum between the positive charges, like the intermolecular inter distance between them is very small. Okay, farther. If they are inside, then there is a very high distance between them, like very small distance. They will repel each other and goes away farther from them and at the sides of the surface. That's why they will come on the surface of a conductor. But in case of insulators, that will not happen. In the case of insulator, the charges will reside inside the whole volume. If you have a volume of any body, then it will reside inside the volume of that body. Why this happens? Because there are very less free electrons inside an insulator, and they will do not want the incoming positive charges to be go repel each other and go farther away from themselves. They will try to bound themselves inside the body, because they don't the insulator have a tendency to do not conduct the electricity or heat. So that is why if charge is given inside them, they will reside inside whole volume. They will not come at the surface, because they don't have the tendency to become conduct electricity. That is why. Okay. So let's move further. Total charge of a conductor lies at the outer surface of a conductor, that I've told you. The magnitude of field strength at any point on the surface of the conductor is proportional to surface charge density at that point. Okay. So magnitude of field strength at any point in the surface of conductor is proportional to surface. It is very it's obvious thing, because if you have charge density sigma is there, it will be directly proportional to q only, because more the q is there, more will sigma is there. Sigma is equal to q by a, and if the q is there high, then sigma will be high. Similarly, if rho is q by volume, so if q is high, then rho will be high. That is already like clear to be like that. It is this obvious thing. Okay, so yeah, let's move further and see what is the next topic. Yes, these are some questions on this topic that we have covered just now. So we will cover all the these like questions in separate lecture that we will see only questions on that lecture. Till now, that lecture will be of exercises only. We will cover here only examples and like theory part. So let's move further and see that what are the next topics and examples in your book. Okay, yeah, these are some examples. So there are many questions in your book. You will see them in like separate lecture. Okay. What is the next topic I have to check? That is electric dipole. Okay. So it is also very like important topic in your book, and it is asked in your boards very much. Also, this is important for your competitive exams also. But you have to be aware of like previous topics also for that. Like you have must have the knowledge of your Coulomb's law and electric field lines and what is electric charge, the basics of that. After that only you can start this topic. If you haven't seen the previous lecture, you might can refer to that, but don't start from here only. Okay, so let's start the topic and see that what is there in this. So electric dipole. What is an electric dipole? So it is a pair of point charges, or it is a pair of you have small charges, and it they form a pair like minus q plus q is there. So should have the equal magnitude and opposite sign direct like charges. Like if you have minus q, then there should must be a charge plus q there to form a dipole. Okay. And so what is the condition to be dipole? Like to form a dipole, what is the necessary condition? That the charges should be of positive, like positive and negative both type, and they should be of equal magnitude, and they are separated by a small distance. The midpoint of location of minus q and plus q is called the center of the dipole. Okay, that is clearly shown in your book that what is the dipole and what how it is represented. So yeah, you can see here that there is a charge minus q placed here and plus q is placed in the right hand side. And there is a dipole center of dipole. This will represent a dipole in the direction of that dipole. We will see in the further lecture that what is the direction of that dipole. Okay. So yeah, let's move further in this topic. Dipole moment of an electric dipole. Okay. Yeah. Just a second. I should move this like this and clear the drawings. Okay. So dipole moment of an electric dipole. Okay. The strength of an electric dipole is measured by a unit vector or a vector quantity known as electric dipole moment. That is represented by P. So if you have a dipole, electric dipole is what which I have told you the like previous topic, that there is a charge minus q and plus q. Two charges are there and they are separated by a small distance having equal magnitude of charges. So if there is a strength between them like electric dipole, which is the strength of that is measured in terms of electric dipole moment, which is represented by small p. And it the separation between the charge should be like a 2L. We will see that why we have taken it as a 2L, because that will make the calculation simpler in the further topics. So minus q and plus q are separated by a 2L distance. So the magnitude of electric dipole would be what? Like P is equal to Q into 2L. Okay. That will be your electric dipole moment. Okay. Electric dipole. Yeah, that is. It is a vector quantity. So dipole moment is what? Your dipole moment is an electric dipole is a vector quantity, and its direction is from always from negative to positive charge. That you should remember that this is important topic, that its direction is always from negative to positive charge. Okay. As I unit of dipole moment is coulomb meter. That is obvious because there is a product of Q and distance. So the SI unit will become coulomb meters. Okay. If charge Q gets larger and the distance PL gets smaller, and keeping the product as PQ2L constant, we get what is called an ideal dipole or pointed dipole. Thus, an ideal dipole is the smallest dipole, I think, almost knows. So, if this is saying that if you have like a distance becoming very small and the charges overlap each other, then it will become a single dipole, or that is almost of negligible size and shape. So, that will become an ideal dipole or point dipole, which is not useful for us. We will not see that type of dipoles. We have the dipoles like they are separated by a small distance and having a small charges minus and plus Q. Physical significance of dipole. Okay, so what is that? Yeah, in some like in most molecules, the center of positive charge and of negative charge lie at the same place, and their dipole moment is zero. Example: CO2, HCH4. Okay, so some of the molecules you have studied in chemistry also, that they have the dipole moment that is equal to zero because they have the linear, they have the straight line shape like that. Because and the dipole due to them will cancel out. If they are in straight line, then dipole due to one charge bond will cancel out the dipole due to other bond. However, they develop a dipole moment when an electric field is applied. But if you apply an electric field, then they will develop some electric field dipole throughout them. But some molecules have permanent dipole moment. Example H2O. So H2O has a V-shape that is the structure. So which that will form a net dipole moment. Okay, that is why this is saying that H2O has some dipole moment. So these are called polar molecules. So if they have some dipole moment, they are called polar molecules. If the center of mass of positive charges coincide with the center of mass of negative charges, molecule behaves as a non-polar. Yeah. So if a center of mass positive charge will coincide with the negative charge, so that will cancel out the net effect and that will become a non-polar molecule. So there is an example a system of two charges having this. You create a point like this and P is equal to this. What are the total charges and dipole moment of the system? Okay. So I hope that you can do this by yourself because this is a very simple question, and you have to find out that what is the value of electric dipole here. So simply you can you can take either charge and multiply the distance between them and get the direction also. Okay. So I hope that you can do this by yourself. If you have any doubt in this question, you can post or comment in the chat box, or you can ask in doubt sessions also. If you want them separately, we will make sure to conduct that also. Okay. Electric field intensity due to an electric dipole. Now, the next topic is like electric field intensity due to an electric dipole. We have studied that electric field is due to point charges and line charges. We have not studied that, but we will see in the further lectures. So, electric field due to intensity due to an electric dipole is what? It is the electric field due to the system of two charges that have minus q and plus q charges that will form a dipole. So dipole has also its electric field. So we will see that what is the electric field due to dipole. Okay. So let us see that if we have to calculate the field intensity at a point P, that is axial. The first point that will cover in the topic of electric field due to an electric dipole is like on the axial point. Okay. So what is axial point? If the point is in the axis, if point is located on the axis of dipole direction is what? From minus q to plus q. So if the point is located in that axis direction only, So that will be what axial point. Like you can see here that these are two charges minus q plus q, and we have to find the directed field intensity at point P that is on the axis of these charges or dipole, that dipole. Okay, that is in the direction of this axis. Okay. So, how to find the electric field on this like this point? That will be if I found out the electric field that will be due to electric dipole EP at EP we due to which charges EA. Due to this charge I have an electric field, and due to this charge also I have electric field on this point. Two charges are there, so I have the two types of electric fields here. So, the direction, what is the direction of electric field due to that charge A? So, A charge has the direction that is equal to like this, because the charge is negative, so EA will be in this direction. EA is like this direction. And what is the direction of EB? EB will be in this direction, because this is positive charge, so the direction of electric field will be like this, outward direction. So if I found out the net vector sum of E and VB, because these are opposite in direction, so net electric field at P will be equal to EB minus EA. I have taken this direction as a positive and this direction as negative. So the net electric field at point T will be what? EB minus EA, because EB has the direction in the positive and EA has the direction in the negative. Okay. So what is the value of EA here? See carefully. EA is what? Like K will be there and Q will be there, because Q and Q are same. So K, Q I have written, and X, well, the distance will be what? Because the distance between two dipoles is like two charges is 2L. Okay. So this distance is be what? If P is a point that is placed here, so it has the distance from this charge that will be equal to X plus L. Okay. Why? Because distance always is taken from the center of the dipole. You have the system of two dipoles minus q and plus q. So it is like a system of like charges. So you must have the like distance from center of the dipole, and it is a distance like 2L between these charges. But this distance is L, and the charge is placed at point P. Like you charge is not placed, like unit test charge is there, because you have the electric field, like you have to find electric field intensity there. So the distance from this charge will be what? This will be this plus this, that is x. Okay, this is x distance. It means that is x distance. Okay, this is x distance from the center, because we have taken from the center, and this distance is L. This distance is L, so this will become what? X plus L. X plus L, and this distance is what? Because this distance is x, so this distance will be x minus L. Okay, so this distance will be x minus L. So from a negative charge, the distance will be x plus L, and the positive charge, the distance will be x minus L. Because the dipole is the system, so we have taken the like distance of that point P from the center of the dipole, and then we have calculated the electric field due to charges P and A. And for like A charge, I have the K q by x plus L square, because the distance between positive negative minus q charge and P point is x plus L, and due to B, that will be equal to K q by x minus L square, because the distance between B and this P point is x minus L. Okay, so here we have now substituted the values. So let's clear the drawings, and then we will see that what is the calculation. Yeah. Yes. So if I substitute the values here, so EA is here. So EP will become what? A I have taken common, like K I have taken common here. So inside the bracket, what will remaining? Q by x minus L square. See here, we have substituted here, and we get it like this: x minus L square minus Q by x plus L square. Okay. Now K will be remaining outside the bracket. and we have to take the LCM here. LCM will be what? A minus B, A plus B, A square minus B square. Okay, A plus B, A minus B, what is the identity? A square minus B square. So X square minus L square, and the whole square will be there because that was previously present square terms. And here, what will be remaining? Here, if you multiply here, so Q will be like that, and here you have X plus L square due to LCM, and here you have the X minus 1 whole square due to the LCM part. And if you calculate it, the X square and one word term will cancel out due to square, like this minus sign, and the term that will be remaining like 2xl from here, and minus of minus 2xl from here, so that will become 4xl. That is why it is written here 4xl, and q was there outside that bracket like this. So 4qxl upon x square minus l square whole square into k will be remaining there. That is written inside this p point, like this point. So many students have the doubt that how the calculation part has come. So I have like clearly defined you that how this is calculated here, and that you have to remember that this calculation or derivation is asked in your boards exam, and also in your school exams also. So hence EP becomes what? K 2pqx upon x square minus l square to the power 2. Okay. Why it is 2px? Because q into 2l is what? Your dipole moment. That will become p, and 2 was remaining there. So 2x is there and p will be there. Okay. This will become p. So 2px upon x square minus l square whole square. So this result you have to be like always remembered, and yes, make sure that you try to solve or derive it by yourself after this lecture. So let's move further in the next topic. Like we will see the next topic. Like, what is that? I will clear this. So here it is said that in vector form, EP is equal to that field we have calculated previously. Vector form, how we can write that? EP is equal to K into 2px upon x square minus l square into x square minus l square whole square. And in a if a dipole is very short, if that dipole is very short, that will what? If that will become 2l is very less than x. Why? Because dipole is very short, so 2l distance is very less than x. Then the this term, that is EP, will become what? EP will become k into 2p x upon x square term, like l square will be like negligible, it will be neglected here. So x square to the power 4, like x square to the power 2 will become x to the power 4, and it will come out to be like that, k 2p upon uh, like uh, uh, x 2, that is written here. Okay, so you have to remember these results. The direction of EP is along BP produced clearly EP direct proportional to 1 by x cube. So direction of EP is along BP here. You can see that in the figure also. And this is the calculation of what at the axial point, the electric field of and dipole due to axial point. Now we will see the calculation for the equatorial point or equatorial line. What is that? We will discuss here. Okay. Okay, let's clear this part. Till now, we have seen that what is the axial point, then what is the equatorial point. So, if the dipole, the point is in the perpendicular direction to the dipole, that will show the equatorial point. Okay, like you have two, just a second, you have two charges minus q and plus q. So the dipole will be like this. Okay. So the axial line is like that. I have shown you. But what is equatorial line? That is perpendicular to the two charges. Or axial line that is perpendicular to the axial line. So this is your equatorial line that will pass through the center of the dipole, and the distance should be measured from this point only. Okay. So let's see and find out what is the calculation here. Consider an electric dipole consisting of two point charges minus q and plus q separated by a small distance AP. So, okay, there is a distance between them AB that is equal to 2L with center at O. So, the center is O, that is your reference point, and dipole moment P is equal to Q2L is shown. So, Q into 2L is the what? Dipole moment like magnitude. Now, let's find out that what is the dipole moment calculation here. What is electric field calculation here? So, uh, electric field due to a charge, like if this charge minus q charge is what? If you see here, that minus q has the direction of electric field along this direction, because it will be in inward direction due to minus q charge, and due to plus q charge that will be in the outward direction EB, like that. So the resultant will come like in between them, and that will be equal to EQ. Okay, that is shown here also. If the angle between them is theta, this angle will be theta, this is theta, then this will be theta, and that is why the direction of the electric field, that is Q, that is net electric field, will be in between them, because 2 theta is the angle between them. 2 theta is the angle. So then due to symmetricity, the electric field, net electric field, will be in the theta direction, like theta angle to the this E. Okay, this E or this E, that angle will be theta. So resultant electric field will be equal to EA plus EB. The vectors EA and EB are acting at angle to theta. There is EA is here KQ by x square plus L square. So why the value of electric field due to A is KQ by x square plus L square? Because this distance is your L, like this will be L and this is X. So due to Pythagoras theorem, this distance, that is the distance between the two chart, like 2 points where we have to find the electric field, that will be equal to root over x square plus L square. And when we square this distance in the denominator, that will become x square plus L square. Similarly, for B point, this distance will be similar to this distance. Okay, root x square plus L square. So after squaring that, we will also get that like that equation that is similar to this one. So E and EB are equal, and that is equal to KQ by x square plus L square. On resolving E and EB into rectangular components, the vector EA sine theta and EB sine theta are equal in magnitude and opposite to each other. Okay. So EA sine theta and EB sine theta are equal and opposite. Here EB is that. If you resolve it, EB will be EB this is EB sine theta, and this is EB cos theta. Okay, this direction EB cos theta, and here you have this EA. So EA EA cos theta is in this direction. Okay, and EA sine theta is in this direction. Okay, EA sine theta. So sine theta term are equal because the electric fields are equal, and sine theta terms are opposite in direction. That EV sine theta is in upward and EF sine theta is downward direction. So that will both will be cancel out to each other, and the net effect of sine components will be 0. Okay, so net effect is due to only cos components, that is equal to EA cos theta plus EB cos theta, and it will become equal to 2EA cos theta. Why? Because the EA and EB values are equal here. I have already told you that these are equal here. And after you simplify it, what you will get, that is equal to 2 into K, that is K. Here 2 is there. 2 is there already. So 2 will be there. Then K term is there. And Q by x square by L square is there because of this. And due to a cos. What is cos theta in this triangle? This is theta. This distance is L. This is x. So cos theta in this triangle will be equal to base upon hypotenuse, and it will be equal to L by x square plus L square to the power half. Okay, if you calculate this, you will get this value only. So try to find out that it is similar to that. So I have written the cos theta value here, and after simplifying, I will get the answer as k through ql upon x square plus l square to the power 3 by 2. Why 3 by 2 power is there? Because x square plus l square power 1 is there and half power is there. If you add 1 by 1, 1 plus 1 by 2, that will come 3 by 2. And q into 2l is p here, that is the dipole moment. So q into 2l will become here c. So the value will come out to be equal to k into p upon x square plus l square to the power 3 by 2. The direction of E is along QE. Okay, that will be in the direction QE because of that opposite to AB in vector form, we can rewrite it. Okay, so I show you why the direction is in the along QE direction. Okay, let's just move it downward. Yeah, QE direction. So this is your Q and this is your point E. So electric field is flowing in this direction only. So that is why the direction is QE. Okay. So yeah. Now we will see that what is the next point in your book. So E at Q due to Q. E at Q is what? Minus P by 4 pi epsilon naught x square plus L square to the power 3 by 2. EQ is in the direction opposite to the direction of P. So here the net electric field at this point is in this direction. That is in the negative direction. Why? Because we have taken this direction as positive. So this direction is negative. That is why the direction sign is negative here. So we have the value minus P. K minus P upon x square plus L square to the power 3 by 2. And if the calculate only magnitude, then it will be equal to mod of P upon 4 pi epsilon naught k x power 3. And why x power 3 is there? Why? Because if we have taken that dipole is very short, then 2L will be negligible and x will be only there. So the term will become like K P upon x square plus L square to the power 3 by 2. Okay, or L square term will be cancel out. So here what will be left? X to the power 2 into 3 by 2. So x to the power 3 will be remaining here. That is why we have written x power 3 here. So EQ is directly proportional to 1 by x cube. So if you have if you have been asked in that exams that what is the relation between electric field at any equatorial point and the x distance between them, so that will be equal to E to the E directly proportional to 1 by x cube. So that you should remember. And here is the result that E axial upon E equatorial is equal to 2. You can find out it by like dividing it. If E axial is that like this, E axial, and you divided by EQ, all the terms are equal, but 2 is there, so 2 will be left out. Okay. Both the magnitude and direction of electric field they depend on not only the direction r but also on the angle between the position vector and dipole moment. Okay, so that will also depend on the position and that position vector and angle between the points where you have to calculate the electric field. We will see the general form also. Relative to a dipole falls off at large distance at a much faster rate than an electric field due to a single charge. Okay, so electric dipole has the electric dipole has the electric field that will fall at much faster rate due to electric field due to a single charge, because there is you can see that relation 1 by r cube is there, and in the electric charge there is a relation of 1 by r square in the electric field, if you remember the equation. So that is why electric dipole has the more significance value. Okay, so till now we have covered many parts today, like what are the properties of electric field lines and some examples of electric field. And after that we have covered the topics like uh, conductors and type of like electric field, what is the pattern of electric field due to a conductor. After that, we have covered dipole moment and what is electric dipole, and electric dipole due to like a system of charges at equatorial point and axial point. So for today, the lecture is I think enough for today, and we will see the next part in the next lecture. Till now, whatever I have told you, you should revise it and try to solve the maximum questions. I will take the question session in the next or after some classes. And I hope that you got all the points which I've told you. If you have any queries or doubts, you can post here, or you can ask for the doubt sessions also. And we will arrange for you private sessions or one-to-one sessions also if you demand for us. So thank you for today's session. Have a great day.